Hello, welcome back to Three-Phase Circuits. In this lesson, we're going to talk about Y-delta problems part 2. It's our second problem in the sequence of Y-delta problems where the load is a delta configured load. So again, this is still a baby problem, but a little more involved than the last problem because there's some core things here I want you to understand before we go on to the more complicated problems. Let's take a look at it. The first problem here is it says a balanced delta load has a B-phase line current of 26 at an angle of negative 50 degrees amps. What is the phase current IAB if the phase sequence is negative? So there's a lot of information that you need to pull out of these words. All of these problems that you have in this class are almost all going to be word problems. You have to draw the circuit yourself. So always reacquaint yourself to what a delta connected load looks like. In fact, I strongly recommend to you that every time you take an exam or quiz or homework, sketch this drawing in the upper right corner somewhere so that you can refer to it. It really helps center yourself with what you're looking at. If you don't have something to refer to at all, then what will usually happen is you'll make a mistake somewhere because you'll forget if you're talking about a line current or a phase current. It's just so easy to avoid that. So here again we have the delta connected load as a triangle, and I've drawn the currents, the line current AA coming in. I haven't drawn them for B and C because it clutters up the drawing, but there's a line current for B and a line current for C. So these are called the line currents, and of course you have the phase currents. These are the loads, the current going through each phase of the load. And the way they're numbered or lettered is AB, BC, CA, right? So let's look at what the problem has given us. A balanced delta load has a B phase line current of 26 angle 50. So the way that you need to realize that or remember that, you need to write down what you know. A B-phase line current. Line currents always look something like little b, big B, because the little b is the kind of the marker we have near the source. Big B is this one over here near the load. So this guy is the line current going through the line, and it's 26 at an angle of negative 50 degrees amps. And of course it's implied, it's always RMS when we're talking about these kinds of things. So if you go over here to the drawing, what you have is this is I, little b, big B, and you now know what this is. It is 26 at an angle of negative 50 degrees amps, RMS. Okay, so now we know. We've deciphered the first sentence in the problem. It's balanced. Okay, that has to be true. It's a B phase. That's what we're talking about. The line current is given as this. That's what we have. Okay, what is the phase current? Blah, 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 blah. We'll talk about the rest in a second. Let's say, what is the phase current? That means what is the current going through the phase of the load, right? So a phase of the load is one of these three phases in the triangle. That's what you need to remember when you see phase load for delta. That's why the drawing is helpful, because you don't want to think of a phase current being over here. These are line currents. These guys going through here is a current going through one of the three phases. So we call it a phase current. So what is the phase current? IAB, capital AB. It even tells you what you want. So you can write that down here. Let me switch colors. AB, capital AB equals question mark, right? So we go over here to the drawing. This is what we want to know. That's the only thing that we care about. However you get to the answer, and actually there's more than one way to do it. I'm going to show you both ways. That's all you care about. You just want to know what this phase current is going through this leg of the load. We don't care about this one. We don't care about this one. We just want to know this one. All right. It also tells us crucially that the phase sequence is negative. That's going to be important because when we choose our sign for our current shifting formula, remember you need to know if it's positive or negative phase sequence. It also is important for other things as well. The first thing we want to do in this problem is draw a little diagram for the phase sequence, especially when it's negative, because that's a very easy way to get a problem wrong for no reason. So because this phase sequence is negative, the way you do it is you say this is the A phase, that's horizontal. And if it were positive phase sequence, it would be A, B, C. This one would be the B phase, but this is a negative phase sequence, so it is A, C, B. So the way you look at it is negative phase sequence A, C, B, right? And I also encourage you to write down, even though I know you can do simple math, to go from A to C, you subtract 120 degrees, and go from A to B, you add 120 degrees. This is going to be helpful, and you'll see why in a second. All right, so what do we actually have here on the board? We know what this line current is, BB. Okay, if the problem were asking us, what is the phase current, BC, See, this is the phase current BC that goes with the line current BB. We know what BB is. If it was asking us what this line current, this phase current was here, the problem would be even simpler. We would just use the phase shifting formula, and we would just calculate directly the square root of 3 formula for the line current shift, or the current shift in the delta load. We've been using it all along. We would just use that, and we would calculate this, and we would be finished. The only wrinkle they throw in it is they don't ask you for this one, they ask you for this one. Okay? So there's actually two ways to proceed in this problem, and you got to think logically about it, okay? And you got to think about what can I do, and then what can I do after I do that, okay, to get to where I want to go. I know what this is, this line current. I know what the phase sequence is. I know a formula that can convert from this line current to this phase current. So if I apply that formula, I will get IBC, and if I do it correctly, I'll have this current. And then, because I know the phase sequence, anytime you have a balanced set of three-phase currents or three-phase voltages, once you have one of them, you have all three of them by adding and subtracting 120, right? Because remember, normally we solve these problems by solving the A phase voltage or current, and then we add or subtract 120. But the same thing is true. If I know any of the three, I can always get the other two. For instance, if I know the B value of this current, that's this one. This is why I draw this diagram. If I know the B value, then to get the A value, I just add 120, because to go from A to B, I said that backwards. To go from A to B, you've added 120. So if I already know the B value, I subtract 120 to go here. And then once I have A, I subtract 120 again to go here. This is why I draw the diagram. This is why I draw the signs here, because I can tell myself mentally, okay, if I got this, I can current shift to get here with the formula. Once I know this value. To get A, I'm going to subtract 120 degrees to get the A value. The A value is what I want. So if I know this phase current BC, I can find AB, boom, I'm done. And that's a totally valid way to do the problem. That's one of the two ways that I'm just thinking about doing this problem. There's another way to do the problem, which is the way we'll actually do the math. Okay? I want this. So instead of going here and then going here, what I can do, these currents, these line currents, AA, BB, and BC, AA, BB, and CC, they also form a three-phase set. I know this current, the B value, so I can find the A value of the line current, again, by using the drawing over here. We'll do it in a second, but I can basically do the 120-degree shift just to get the A line current, just because I know it's a three-phase set. Once I know this, I can shift from here to here using the square root of 3 formula, because this is the A value line current, this is the A phase line current, this is the A phase voltage. So I can shift between these two with the square root of 3 formula. So in the one way of the problem, I shift using the square root of 3, and then I plus or minus 120 to get here. In the other way, I go shift here and then go here secondarily. So there's actually two equivalent ways to attack this problem. Let's go ahead and do it all the way through with one of them, and then we'll go circle back and talk about how we could have done it a different way, right? So we know what BB is. That means we know what this line current is. It's a balanced three-phase set, so I can easily find the A line current by what? Going from here to here, I would have to I'd have to subtract 120, because going from here to here is adding 120, so to go the other way, I'd have to subtract 120. So that's what I'm going to do. We're going to start over here, and we will then say I little a big A is equal to the same magnitude, 26, angle, phase, we start out with negative 50. That means we have this guy, we have to subtract 120, minus 120 degrees. So I little a big A is 26 at an angle of negative 170 degrees. Amps RMS. Okay, so now I've gotten the line current for the A phase, which is what I want because I'm asked for the phase current of the A phase. AB is for the A phase, right? So AA goes with AB. I know this current now, and now I want to find this one. How do I convert between phase and line currents in a delta load? I use my square root of 3 shifting formula that we've been using all this time. So that's what we're going to do. So now I know that I little a big A is equal to, this is the line current, is the square root of 3 times the phase current, AB. And then I have minus plus 30 degrees. And then I have to ask myself, it's a negative phase sequence, right? From the problem statement, negative phase sequence. So if it were positive phase sequence, I'd choose this. Negative phase sequence means I choose this. So I erase the top sign. It's going to be a positive 30-degree phase shift. If I were calculating this, if I knew what this was, I would stick it in there and I'd multiply this stuff and this is what I would get. But in this case, I already know what this is and I want to find this. So I need to go backwards and flip everything around. And this is another opportunity for people to screw things up. It's very easy to do. But what we're going to do is take it one step at a time. IAA is 26 at an angle. It's not a negative 50 degree angle. We already found it. It's negative 170. So negative 170 degrees, square root of 3, I, capital A, capital B, plus 30 degree phase shift. Okay? So how do I then find this quantity? I need to divide by square root of 3 and then divide by this phasor. So let's go ahead and do that like this. We'll say that I, capital A, capital B is equal to 26 angle negative 170. On the bottom, square root of 3. And then I have this phasor here, plus 30. Now there's a couple of ways you can tackle this to actually do the calculation. You could literally take your calculator and just stick this phasor in the numerator, 26 at an angle of negative 170, and then you make a new phasor with a magnitude square root of 3 and a phase angle of plus 30, and you divide those two phasors. That's perfectly fine to do. But what we're going to do is think about it a little bit more and give you some practice with manipulating these. Okay, so you can divide these things here. That's no problem. You can, of course, do that. But I want to show you, if you were doing it on paper, what you'll see a lot of times in books is something like this. You'll have the 1 over square root of 3 term, right, because of the 1 over square root of 3, and you'll multiply it. Let me do it with a bracket. 26 at an angle negative 170, right? That's exactly what all of this stuff is. Now this is the problem, not really a problem, but you want to get it out of the denominator and you move it upstairs and make it negative 30. And the reason you move it upstairs and make it negative 30 is what I've said about a dozen times before. This is an exponential. It's a complex exponential. So is this. So any exponential on the bottom, when you move it upstairs, you make it negative. That's why you do that. So think about what you're doing, though. If you do it as a division, then when you divide, when you have an exponent on the top and an exponent on the bottom, you subtract the exponent. So 170 minus 30 would give you the negative 200 there. Once you move this guys upstairs, then you're going to be adding these guys, which also give you negative 200. So either way you do it, it's fine. If you want to do it in your calculator like that, that's fine. A lot of books will show it as 1 over square root of 3 times this, and then it'll have the negative of what you expect, because you start with this, and then the problem will have this, and then so a lot of students get confused. Why did it change the negative? It's just because you divided by that phasor, which changes the sign of the phase shift if you keep it upstairs like this. So the bottom line at the end of the day, let me switch colors. Finally, after all of that talking, we'll get to the answer. Actually, let me switch to the next board. I, capital AB, when you do all of that stuff, you're going to get 15.01 at an angle, as we already said, negative 200 amps, RMS. All right, this is perfectly fine. You can subtract this, but it looks a little weird to have really big phase angles like this, because if you think about it, what you have is a unit circle. You've started here and you're going negative because this is a negative answer, right? So you have negative 180, and then you even went past that and you're way over here. It makes a lot more sense to represent an angle like this, not by negative 200, but as a positive, smaller angle. So it's totally fine. If I would give you full credit if it were me, but I'm just saying some people would like to take this, and when you want to convert things, you can add 360 to it. So what you can say is IAB is 15.01 angle negative 200 plus 360. You're totally allowed to do that. Of course, you know that. And then IAB, 15.01 angle, what do we get here? Positive 160 degrees, amps. Which makes sense, because if this were negative 200, then this would be around 160 going the other way. This is what I would circle, but this is perfectly fine to circle also. So let's just take, this is a baby problem, it's not a real problem, but let's just kind of take stock of what we did really quickly, because it's important. You're going to be doing this a lot when you do your real problems. We know we were given what the line current for the B phase was, this guy. Okay, we were asked to find the phase current AB. So to do that, what we did is we shifted, knowing the phase sequence, from B to A to get the line current up here. We did this because we knew this guy, so we subtract 120 to get the A phase. Once we have this, you can go back and forth between the line current and the phase current in a particular phase by using this equation, which is written line current, square root of 3, phase current with a phase shift, right? But we didn't know this, we're solving for this, so we put the value we know in, we move the square root of 3 over, we move the phase shift over, which brings it upstairs as a negative, and we divide by square root of 3, we multiply all this stuff, and then we got the answer, and then of course it was such a big negative number, bigger than 180, we elected to add 360 to it to get the answer. That's one way of doing it, no problem. Just so you know, it's totally valid to do it the other way. Instead of going from here to here to here, it's totally fine to go from here to here to here. Both will give you exactly the same thing. I encourage you to get a sheet of paper out and prove that to yourself. If you were to convert from BB to the phase current for the B phase, BC, how would you do it? Well, you would use the exact same formula. You would use this one, except it would be BB here and it would be BC here. The phase shift stays the same. The square root of 3 stays the same. So what you would end up doing is you would take this guy, which was negative 50, you would go through these calculations, and you would end up subtracting 30 degrees from its phase angle, what you had here. So you would subtract 30 degrees, which would give you negative 80. So the answer here, you can just see by looking at it, is going to be the magnitude of whatever it is, okay, the same exact magnitude that we got over here. Then you would, the phase shift here, going from here to here, would be this magnitude actually. This divided by the square root of 3. This phase shift over here would be negative 80 because we're phase shifting by, we subtract 30 degrees from the phase shift. Now to go from here to here, what do? You start from B, then to go to A, you have to subtract 120. So we said the phase angle here was going to be negative 80. We already just kind of mentally did that. And then what do? We add one, let's see, we subtract 120 to get here. Subtract 120. So negative 80 minus 120 gives us negative 200. So going through the mental gymnastics, going this path, we have negative 200 for the phase angle. That's exactly what we got the other way. So you're getting the same answer either way. So whether you subtract the 30 and then do the other calculation, or do the other calculation, do the other calculation, you get the same exact thing either way. There's more than one way to solve any problem. So all of this math involves adding and subtracting numbers, basically. It's not difficult, but if you don't know what a phase current is and a line current and how to use the equations and how to manipulate the equations, you'll never get the right answer for such a very simple type of idea. So let's go on to the next lesson. We're going to ratchet up the complexity of these problems a little bit as we go along with 3 phase circuits.